Hello everybody, here is your video introduction to polynomials. Period 3, please see this note here. Period 7, you're watching this entire thing because all you did is tape these in your notebook. If these are not taped in your notebook, this one goes first, and then this little one's going to go second. Alright, so let's talk about what a polynomial is here. So this is only period 7 right now. I've been saying the word polynomial, and I never actually gave you a formal definition of it. So a polynomial is the sum. Sum just means you're adding. And you add up monomial terms. Now monomial, mono is a prefix for one, so you just add up individual terms and you get a polynomial. But there are a couple rules here for a function to be a polynomial. First of all, you must have whole number positive exponents. And second of all, you should have terms that are written in decreasing order of exponents. And one last thing, in order for the graph of a function to be a graph of a polynomial, the graph needs to be continuous. And that kind of sounds like what the word indicates here. Continuous means it never ends. You never have to pick up your pencil to draw it. An informal definition is you can draw it without lifting your pencil. And a slightly more formal definition is you cannot have any gaps, holes, or jumps. There is a really formal definition of it, but that is for higher level math. So for now, just if you draw your graph without lifting your pencil, you're good to go. And another thing is polynomials are smooth curves. There are no sharp points. Now, functions that you've seen before with a sharp point would be like an absolute value graph like that. So we can't have any sharp points like that. The next thing to know about polynomials is we classify them by something called the degree. And the degree is the highest exponent. So I'm going to write down two polynomials here, and I want you to write them down with me. And we're going to talk about a few features that you're going to need to pay close attention to because later on when we get more in depth with polynomials, they're going to play a big part in what we do. So first of all, if the degree is the highest exponent, then the degree of the first one is going to be a 5, and the degree of the second one is a 4. Two things to notice is you can skip exponents. So like I skipped 3 here. I'm skipping 3 and 2 here. Second thing is notice my exponents go in decreasing order, so it's in standard form, we say. So this is your degree, and this is your degree. Now the leading coefficient is going to play a big part in polynomials. Leading means it's first, not necessarily biggest, but first. And I'm abbreviating because I'm almost out of room. And the leading coefficient of the second one is the 5. The last number that's going to play a pretty big role here is the constant. And constant, think no variable. That's going to be the number at the end. Now, if there's no number at the end, like let's say this wasn't there, the constant of this polynomial would be 0. But this one does have a 1 there, so we're going to say 1 is the constant. So now I'm going to write down two non-examples, and I want you to think, as you're writing this down, why are these non-examples? So 3x to the 1/3 minus 4x minus 7 and 7 over x squared plus 3x plus 2. Now the first one might jump out at you and it's like, well, duh, if you have to have whole number exponents, that's definitely not a whole number. So that's the problem. But when you look at the second one, the exponent here is a 1, by the way. That's positive. That's positive. They're whole numbers. So the question is, why am I saying that this whole thing, I should say, can't be a polynomial? These two terms are fine. It's really this one. And even though the 2 right now is positive and a whole number, if you wrote it so it didn't have a denominator in the more standard way of writing things, to force it in the numerator, it would become -2 as an exponent. And now this breaks the rule because I have a negative exponent. Okay, so let's keep moving here. Let's talk about polynomial types. So this chart's just going through the degrees, and you need to know all the different names here. You know pretty much all of them except the last 2. Now, if I have a degree of 0, I want you to think for a minute, what would a polynomial of degree 0 even be? And what does a degree of 0 do? So think, if you have something raised to the 0 power, because degree is an exponent, something to the 0 power is always, and hopefully in your mind you said 1. So if I had like 2x to the 0 power, well, x to the 0, that's just 1, and 2 times 1 is 2. And if I had said, hey, what does y equal 2 look like? You should be able to tell me it's just, don't just say it's a line because all these are lines here. It's a horizontal line. And the type here, since it's just equal to a constant number, the type is a constant function. Degree 1, there's infinitely many possibilities, but what about that? Y equals negative 2x plus 1. The type of function here, you've been seeing these for a long time now, linear. And a quick sketch of that. There we go, just a line. All right, now let's go to 2. I'm going to make up a quadratic with a degree of 2. If you want to make up your own, you can go ahead and make up your own. Let's do 3x squared minus 1. The type of this is what we just spent 2 months going in depth with. It's a quadratic. And minus 1 moves it down 1. 3 makes it narrow. There we go. It's a parabola. How about a degree of 3? Well, that would be, let's do 2x cubed minus x plus 1. That works. Now, the name of this is a cubic, which is what the next video is going to focus on, is how you graph these. You already know how to factor cubics. We just spent a week you practicing that for homework. Now, cubics can be several different things. The most basic cubic is going to look like this. A slightly curved function. The most complicated cubics would be something like, this is just one possibility, remember, something like this. Now I want you to notice something here. A quadratic, which is degree 2, can have at most 2 exponents. A linear with degree 1 can have at most 1 x-intercept. Degree 0 has no x-intercepts. Degree 3 can have at most 3 x-intercepts. You could just have 1 x-intercept. Like this has no x-intercepts. Just like a parabola could have 0 x-intercepts. The degree tells you the most amount of x-intercepts, and there is a theorem for that, which we will slowly get to. All right, degree 4, almost there. Let's do negative x to the 4th minus x. That's just an example. A 4th degree is called a quartic. Just like a quarter is a fourth of a dollar, a quartic is 4th degree. Now, quartics can be many different things. A very, very basic quartic, just x to the 4th, would look something like this, almost like a parabola. A quartic could look something like this, a swoopy W, or even a swoopy M. Now, 4th degree can have at most 4 x-intercepts. You could have just 1, you could have 2. 5 and up, technically if the degree is 5, it's called a quintic. But in general, we just call these guys, anything 5 and up is generally just, it's a polynomial. And there are so many possibilities for the graphs that I'm not even going to fill that out there. Alright, so let's talk about evaluating. So period 7, you're still in with me here. Squeeze this in somewhere. Evaluating a polynomial. Now you've seen function notation before. We've already reviewed this, but I need to make sure that when we get to this, you're going to be 100% comfortable with it because you will have some bookwork on it, and we're going to be evaluating polynomials a lot when we graph these. Let's say I have the polynomial, I'm just going to make something up here, 2x cubed, let's do minus 8x squared plus 3x minus 1. If I said, hey, why don't you find f of 2 and f of negative 2? I want you to pause the video and do it without a calculator because you guys are more than capable of doing it without a calculator. So pause now and then we'll check in and see how you did. Alright, so whenever you evaluated the function at 2 and negative 2, for the first one you should have ended up with negative 11 and the second one negative 55, giving us these order pairs right here. One last thing that you need to do is figure out the end behavior chart here, which I'll be doing with you. You can't graph a polynomial if you don't know the end behavior. So what I'm going to do is something on the graphing calculator, and I'm going to graph each set of these one at a time. And I want you to notice what is the same about each set that I'm circling here. So let's look at the first one here. First of all the degrees are even. And second of all the leading coefficients are positive. So I'm going to go to my graph here, and let's go ahead and zoom standard these. There's the first one, the next one, and the Third one. So one thing that should stand out is that they basically all have the same general shape. The only thing that's changing is how narrow or wide they are. And the end behavior, by end behavior, I mean what the function is doing as you're going to the left forever and to the right forever. This end is going to keep going up, and this end is going to keep going up. So what I'm going to say is if the degree is even and degree is n, so even degree, and if the leading coefficient, which is a, is positive, my ends are going to look like this. I can't really say for sure what's happening in the middle. You could have any kind of curves going on there. But in general, a even degree positive leading coefficient function will have ends that both point up. So an example of this would be like 4x to the fourth minus 3x squared plus 1. All right, I'm going to have this one graphed next. So here I have all these graphed. So I have degree 4, 6, and 8. All the leading coefficients are negative here, so you might be able to predict what's going to happen. Both ends are still doing the same thing. It's just instead of both pointing up, they're both pointing down. And that's because the leading coefficient is negative. But because the degrees are even, both ends are doing the same thing. So as I go to the left forever, I'm going to continue going down. As I go to the right forever, I'm going to continue going down. So let's find that box. We have even degrees, negative leading coefficient. So here's my negative leading coefficient. Here's my even degree. Both ends go down. Anything could be happening in the middle. I'm not sure. But all I care about is the end. So an example of this would be like negative 4x to the 6th minus 3x squared. Something like that. Okay, let's take a look at this set. All my degrees are odd, and the degree here is 1, remember, which is odd. And all my leading coefficients are negative. So I'm going to get that graphed. Okay, so again, odd degree, negative leading coefficient. So there's the first one. Here's a one of first degree. It's just a line, which makes sense. Degree 1 is a line. And there's the next one. So all of these generally have the same shape, except for the line one. If I bump that up to like 3x to the, let's go crazy. Let's do like 15 here. And, woo, there we go. There's a 15 one. It's just really, really steep and really, really flat right there. Okay, so notice, again, I'm focusing on the ends here. As I go to the left forever, it goes up. As I go to the right forever, it goes down. So let's go to our table here. And I want an odd degree and a negative leading coefficient. So that looked like this. And again, I'm just generalizing it off of there. I don't know what goes on in the middle. And an example of that would be like negative 4x to the 7th plus 3x. Something like that. And for the last one, I have odd degrees. And all my leading coefficients here are positive numbers. That one's a 1. So if I go to my calculator, I have degrees 3, 9, and 11. And it's going to graph. Notice these two, the pink and the red, are so similar that you can barely tell them apart. And the blue one, which has the smallest degree, is slightly less steep here. So again, towards the left it's going down, towards the right it's going up. So I have an odd degree with a positive leading coefficient. Towards the left it goes down and does something in the middle. Towards the right it goes up. And a sample example, I need a positive leading coefficient. Let's do like 5x to the 7 minus 3x squared. Alright, so this is the end of the polynomial video, and the next thing we're going to do is how to graph a cubic using the end behavior and the polynomial notes. See ya!